So what I would like to do, just one last thing, about the implicit derivative, which is what we were talking about last time. Implicit derivative. Remember, this is the one where you take the derivative of everything on both sides of an equation and then solve after the fact for dy dx, or for y prime if you want to call it that. This I had intended to do like this one last thing. I intended to talk about it last time, but we didn't quite make it, so I'll squeeze it in now. I would like to talk about the power rule. The power rule for fractions. All right? This is something that I mentioned. You know, everybody knows this is the power rule, right? And this basic rule here, everybody should have this memorized. You probably do. This is how you take the derivative of a power of x. And for which numbers n does this work for? This works for any real number n. It could be a whole number, positive or negative. It could be a fraction. It could even be an irrational number. The formula is still true. Although, we have only, in this class, I've been trying to kind of build everything from the ground up. Really, we have only discussed why this is true when n is a whole number. What I would like to talk about for the next, this won't take long, 5-10 minutes, is why should you believe me when I say this is true, even for fractions, all right? So I would like to discuss this for fractions. So it does work for any real number, but let's demonstrate it for fractions. We have already demonstrated it for any whole number, but not for any fractions. I just sort of told you, and you all believed me, I hope, because I'm a trustworthy guy. I would like to actually talk about why this is true when the n is a fraction, okay? A fraction of whole numbers, of course. I don't mean like pi over 2. I mean some whole number over some whole number. So let's consider y equals x to the power p over q, where p and q are whole numbers. P and q are integers. That's the fancy word for whole numbers, positive or negative. P and q are integers, and I'm looking at x to the power p over q. Can we find the derivative? I mean, we already know what the answer is supposed to be, so I'm going to say we'll show that dy dx, it better be p over q times x to the power p over q minus 1, right? That's what it has to end up being eventually. It'll be a little journey to get there, but it's not a whole lot. It's a nice example of doing the implicit derivative, though. That's why I want to talk about this right now. All right? So when you begin this thing, we start with y equals x to the p over q. This doesn't really look like an implicit derivative kind of situation. Remember, the implicit derivative is used when you have some kind of weird combination of the x's and y's on both sides of the equation. But this equation is actually just solved for y already. So it's, in a sense, not necessary to do the implicit derivative. But the whole point of this is we're trying to imagine that we don't already know what the derivative on the right side is. So the trick here is we're going to do the qth power on both sides. All right? The result will be y to the q equals, what's the right-hand side going to say when I raise everything to the q? I'll write it this way first. P over q, the whole thing to the q. Can anyone remember how to simplify that? What's it going to be? Yeah? Yeah, in this case, you multiply those exponents. So the new exponent will be x to the power p over q times q. So the q's will cancel, and you just get x to the p. All right? So I'm going to start there. Y to the q equals x to the p. And then I'm going to do the implicit derivative. It is necessary to do the implicit this time because I have that weird y to the q on the left side. All right? But I hope you remember how to do this. We talked about it last time. Anyone recall, what is the derivative, the implicit derivative? How about the right-hand side? I'll do the right-hand side. This is the easy one. X to the power p. The derivative is p x to the p minus 1. All right? The implicit derivative, remember, it works exactly like the ordinary derivative, only you just have to remember when you take the derivative of a y, you always have to multiply by dy dx. So what about the left side? Anyone think you can tell me? What's the derivative on the left side? X to the p became that thing. What about y to the q? Nobody wants to say it, but it probably is what you think it is. It's not. There's no funny business, really. What do you think? Yeah. Excellent. Q times y to the q minus 1, and one little thing. Yeah, then times dy dx. Yeah, great. You have to multiply times dy dx. Remember, this is in some sense another version of the chain rule. You imagine the y as some kind of mystery function on the inside. So you have to multiply by its derivative. All right, from here I can solve for dy dx, which is typically what we do next. Solve for dy dx, right? And in this case, all you got to do is I'm going to divide all this business to the other side of the formula, right? They're being multiplied on the left side there, so I have to divide it to get it to the other side. And I think what I end up with is dy dx equals px to the p minus 1 divided by q y to the q minus 1, right? This is the derivative, although it's a little unsatisfying because it has y's in it inside the answer. Really, I wanted the answer to, remember, I'm hoping to end up with this eventually, with only x's on the right side. Sorry, slightly off the top, right? This is what I want to end up with eventually. The way to get there with no y's is I'm going to resubstitute this y. I'm going to plug in x equals p over q, because I want my answer fully expressed in terms of y. So now I'm going to plug y equals x to the p over q. And what should we get? We get px to the p minus 1 over q. And here, x to the p over q to the q minus 1. All right? And now I'm just going to do a bunch of simplifying, and hopefully everything will work out the way I want. First of all, on the bottom, we can multiply the exponents. Whenever you have an exponent inside of another exponent, you multiply the exponent. So up top, I'm going to leave p x to the p minus 1. On the bottom, q. And then it's going to be x. Now, unfortunately, they don't directly cancel here. It's just going to say p over q, I guess, times q minus 1. I don't know. There's not really a better way to write that at this point, at least. But I can distribute there inside that exponent p over q times q, and then minus p over q times 1. That's going to look like p x to the p minus 1, and on the bottom q, and then x. All right. Distributing right here, I go p over q times q, which is p, and then minus p over q times 1, which is p over q. We're getting anywhere here? Any thoughts? What can I do next to further simplify this? Maybe can I do something with that? I like this p over q the way it is. What about the rest of it here? All of this stuff? Isn't there some way I could express all of that as just a single power of x? How would I do that? I remember the rules here. Like if it was, I mean, this is complicated looking, but if it was something like x to the 7 over x to the 9, what would you do with that? Yeah, you would subtract the exponents. It would end up being x to the 7 minus 9. Right? So that's what I'm going to do. Inside the red circle there, subtract the exponents. The top one minus the bottom one. It's going to end up being just x to a single power. It is the top exponent, p minus 1, minus the bottom exponent. Making sure I put my parentheses in the right spots. And then this can simplify right distribute the minus sign there, the p's will cancel. I end up with p over q x to the minus 1 plus p over q, which if you prefer I can just change the order around. X to the p over q minus 1. How do you like that? This is what we wanted to end up with, right? After all that simplifying, this is it. So just to summarize, dy dx is p over q x to the p over q minus 1. Shun, right? That's what I said we were going to demonstrate. You bring the exponent, it's the usual rule for the derivative. It works for any fraction, all right? Because of the implicit derivative business. So the only case of the power rule that we haven't demonstrated fully is when the exponent is an irrational number. Then it's a little bit, trickier to demonstrate this power rule formula. But I think I'm satisfied with the fractions, right? This allows you to handle basically any function that you typically encounter. The times when we want to use fractions in the exponent is when we're dealing with square roots and cube roots and such. Those are all rational exponents still. They're all fractions. Irrational exponents are very strange indeed. All right. Any thoughts about that? This is all I wanted to do in terms of like new stuff for today. This I had hoped to do last time, but didn't quite make it in. All right. So, what I got for today is I made up a cute little review sheet with a bunch of review type problems on it to help prepare for the test. I thought, I don't have a big sort of show planned for you today. I thought I would hand out the sheet, take a look at it. If there are particular ones that you see on here that don't look familiar to you or you are confused about, then I would be happy to go over them in detail. I'm going to do this first so I don't infect you, although I don't think I have the hand COVID, at least. I hope not. Mm-hmm. We can also talk about homework problems if you like. If there are ones, the homework that's due today, those problems you should expect something like that might be on the test. So if there are ones that don't make any sense to you at all, I'd be happy to chat about them right now. Well, I didn't bring my book. So that doesn't make sense. This is a good question. People have been asking me, do I need to simplify my answer on the homework? And the answer generally is no. You don't have to simplify. If they ask you to find the derivative, just find the derivative. You don't have to, especially like after you did the quotient rule or the chain rule, sometimes it's a real pain to simplify after that. I say don't bother. Although if you look up the answer in the back of the book, they will have some weird simplified form of it. Okay, so what you see, everybody got one? What you see on the paper is just a bunch of problems here. I will draw your attention at the bottom of the second page there. So one thing I pointed out, no implicit derivative. That's the last section that we just talked about. But I like to put things on the homework before they go on the test. And the implicit derivative I left off of the homework because we already had plenty of stuff. So no implicit derivative on the test. That stuff will be rolled into the next homework assignment, and then it'll be on the the test. The next test. All right. And then there's a list of formulas to remember. These are the ones that I could think of to put on the list. The point slope form of a line. Sometimes you need that if I ask you to find the tangent line. The basic trig stuff, the sine and cosine of special angles. You should know the definitions of the other trig functions in terms of the secant is 1 over cosine. Those you should know their definitions. You don't have to memorize the derivatives of them. You also need to know the definition of the derivative. It's that limit thing. You should know the power rule, the product rule, the quotient rule, the chain rule. And then you should know the derivative of sine and cosine, like I said, but not the other ones. Those are all the formulas I think that I would expect you to know. Does anybody feel like I left something off of the list? All right, great. Yeah, there's no no calculators or notes or anything. The format of the test will be similar to our quizzes, although I'm gonna like type it up and hand it out to everybody. But I write the question, you write the answer. There's no multiple choice or any of that stuff. Anybody have any questions about like the format of the test? I'll give it out at the beginning, and we'll have the whole time on Friday to do it. I don't intend to make it like really long. Like in general, I don't especially care if you can do these things really fast. So I'm not going to try to like make you cram it all in. Anybody have questions? Nope. All right, you want to talk about any of these topics? Anything look unfamiliar to anybody, or things about the homework? I can talk about whatever you all want to talk about. If you see one on the paper, I think I'm going to leave these ones on the paper for you all to do, but I would be happy to just invent another one just like it, and we can do it. And I got nothing more to say.